Hello everyone, I'm Harini R from Sri Venkateshwara College of Engineering, Bengaluru from the Department of ACE. Subject Digital Signal Processing. Now I'm going to discuss about the topic classifications of signals. Introduction to signal classifications. Signals are essential in various fields such as engineering, communications, and data processing. Understanding signal classifications helps in analyzing and processing them effectively. This presentation will explore different types of signals based on various criteria. Continuous versus discrete signals. Continuous signals are defined for every time value and are often represented by continuous functions. Discrete signals are defined only at specific intervals and are a sequence of numbers or samples. The distinction impacts how signals are processed and analyzed in digital systems. Deterministic versus random signals. Deterministic signals can be precisely described by mathematical equations or algorithms. Random signals, on the other hand, cannot be predicted and exhibit some level of uncertainty. This classification is crucial for applications in communication systems and noise analysis. Periodic versus aperiodic signals. Periodic signals repeat themselves over a fixed period and can be analyzed using Fourier series. Aperiodic signals do not exhibit repetition, making them more complex to analyze. The periodicity of a signal significantly affects its frequency domain representation. Analog versus digital signals. Analog signals are continuous in both time and amplitude, representing real world phenomena. Digital signals are discrete in time and amplitude, making them suitable for computer processing. The transition from analog to digital signals has revolutionized many technologies. Energy versus power signals. Energy signals have finite energy and zero average power over time, typically lasting for a limited duration. Power signals have infinite energy but finite average power, usually representing periodic or long duration signals. This classification helps in understanding signal behavior over time for various applications. Even versus odd signals. Even signals are symmetric around the vertical axis and can be represented as a function of time. Odd signals have rotational symmetry and can be expressed as an odd function. Recognizing these properties simplifies the analysis of signals in the frequency domain. Real versus complex signals. Real signals consist of real valued amplitudes and are the most common in practical applications. Complex signals include both real and imaginary components often used in advanced signal processing. Complex representation is particularly useful for analyzing signals in the frequency domain. Causal versus non-causal signals. Causal signals are defined only for present and past time values representing real-time systems. Non-causal signals can be defined for future time values, often used in theoretical scenarios. This classification is critical in system design and stability analysis. Advantages: improved signal processing. Classification of signals enables efficient signal processing, analysis and interpretation. Enhanced signal quality. Classification helps identify and separate noise from the original signal, leading to improved signal quality. Increased efficiency. Automated classification of signals reduces manual effort and increases processing speed. Disadvantages. Complexity. Classification of signals can be computationally intensive and complex, requiring significant expertise and resources. Noise and interference. Noise and interference can affect signal quality, making classification more challenging. Limited generalizability. Classification models may not generalize well to new, unseen data, requiring continuous updating and refinement. Applications. Biomedical signal processing. Classification of signals is used in biomedical signal processing to diagnose diseases such as ECG signal classification for heart disease diagnosis. Image processing. Signal classification is used in image processing to classify images into different categories such as object recognition, facial recognition, and image segmentation. Environmental monitoring. Signal classification is used in environmental monitoring systems to classify environmental signals into different categories such as air quality monitoring and water quality monitoring. Conclusion. Understanding signal classifications is fundamental for engineers and researchers in various domains. Each classification provides insights that can influence signal processing techniques and system design. Future advancements in technology will continue to evolve our understanding and use of signal classifications. Thank you.